It's now time for Glenn Pietila, subject matter expert, propulsion system sound quality, virtually connected from General Motors in Detroit, Michigan. In his presentation, Glenn will talk about how a NVH driving simulator has been integrated into the vehicle development process, highlighting several areas for improved representation of difficult noise and vibration issues. Thank you, Glenn.
All right, thanks a lot. Thanks for the kind introduction. I'm joining remotely from kind of the Detroit area, so unfortunately I couldn't join in person in Italy, but it's I appreciate the opportunity to present remotely. So I'll start with that. I'll start with the presentation here. So hopefully you see my screen. If not, somebody please speak up and let me know. But I will, I'll talk a little bit over the next 10 or so minutes about the Immersive NV driving simulator and how it has helped us and really helps enable hardware reduction. So as we go through this presentation, I'll start out with a little bit of a discussion about the motivation for hardware reduction. Why do we want to do it? I think in a lot of cases it's obvious, but it's worth talking about. And then go on to how the interactive NV simulator enables that, but then close out the presentation with a quick little discussion about some of the challenges looking forward, right? If we use this idea of using the NV simulator to reduce or eventually eliminate hardware, what are some of the challenges that we have to solve looking forward? So to start out on this motivation slide, I think this is it's a pretty simple slide, pretty simple schematic, talks through what is probably a typical historical vehicle development process, I would say realistically at probably every OEM. And just to walk through the slide, the blue bar is all pre-production vehicle development, and the output of that feeds into this little green bar here, which would be the production development, so hard tooling, production assembly. But if we focus on the pre-production vehicle development process, it typically has some form of pre-production vehicle development or component development, right? A lot of times those components are built using soft tooling. A lot of times they're built using some labor-intensive component assembly. Those eventually go into a limited run assembly process. Again, typically not a production environment, so it's kind of a station build type of offline environment. Sometimes it is really reworking in garages. Those vehicles that are built using that process, obviously it takes a fair amount of time, but they go into physical testing. So a lot of times at a proving grounds, but the vehicles themselves are built from low fidelity parts, right? Again, they're soft tooling, so it's not, the tooling itself is not tuned. A lot of times things like acoustic packages aren't sealed entirely correctly. Mounts aren't fully developed, so the mounts themselves aren't isolating as they should be. And then the vehicle, especially before production, it's camoed. So there's some form of maybe cladding on the outside, some cladding on the inside. All of that stuff prevents N&V engineers from getting really good measurements of those vehicles. Of course, it helps in terms of identifying problems and issues with those vehicles themselves, but the vehicles themselves aren't very representative of what the production intent is. And it's mainly because they're these kind of low fidelity early development parts. After physical testing and some development, those vehicles then may cycle back to get rebuilt in a garage, right? Some components are swapped out with new ones, or eventually the vehicle itself is scrapped, right? Scrapped and recycled, is crushed and recycled as much as possible. But the point of this whole diagram is to highlight that during the pre-production portion of vehicle development, there's a lot of wasted time, a lot of wasted energy, and wasted material, right? The end result of the entire thing is really an understanding of what the production vehicle design should be and how the components should be tuned. But the end result of all the materials here is either scrap or recycle. So I think most of you who've been through the process see that and say, yeah, that's the way it is, but it really has to be, right? I agree, it generates waste, but it's necessary. And I think the goal of this slide, and I think the goal of where we are as an industry, is to start to challenge that premise and to say, what can we do to either at least reduce this pre-production vehicle development, but then eventually eliminate it, right? So as an example, just to splash something up, hopefully most of you are familiar with the Hummer EV, but it's been stated, and really the development of this vehicle from all the way from concept to production was in the neighborhood of 2 to 2.5 years, right? Which is about half of what a typical vehicle development process is. And a big part of what enabled that is this NV drive-in simulation. So just to kind of highlight how it came into the development process, if we think about the left side of the plot, right, early in concept development, this is a point where there's typically a lot of benchmarking done. We go and find competitive vehicles or vehicles that we build ourselves that are representative and set targets that way. In this case, there's nothing like it in the world, right? So there's no competitive vehicle, there's no in-house vehicle that really represented of what the Hummer EV would be. So it was necessary to really develop all the targets, do all the target setting in an NV driving simulator. So we used that tool, brought in different road and wind noises, right, based on what we'd expect from the tire design, from the suspension and the body structure, and also bringing in different drive unit tonal levels, right? As we were going through the development, there's an expectation of what orders would be coming out of the drive unit. We set some different levels from that and built multiple models that let us virtually drive the car before it ever existed. Doing that let us bring all the program leadership into the room and agree on what the target should be for this vehicle at the driver's ear. Then as we go through the vehicle development process, once those targets are set and all the components and subsystems are being developed, we could then take those into status assessments in a virtual manner, right? If you use some of our math tools, analytical CAE tools, to predict what the drive unit tones would be, to predict what the road noise would be, we can bring those performance aspects from a sound and from a vibration perspective into the simulator, and again let the program leadership subjectively drive those vehicles, again virtually before they exist. In this manner, they can drive it. We can start to identify, are there issues that we have to work on? If a drive unit tone is slightly over a target, is that a problem? How much is that problem worth? So we can start to get into a lot of those contenting decisions, again, kind of in the virtual world. Then if we carry it all the way to the right side of the plot, going into production, there were some development vehicles built in this case, and I would call it very few, right? Significantly fewer than would be typically done in a vehicle development process. Those vehicles were used to continue to develop the vehicle, but of course, because there are so few, time on them is really challenged. So we could then take a limited time on the hardware vehicle and bring learnings back into the simulator and continue development that way. So in a lot of ways, the use of the simulator let us do these virtual evaluations and really communicate NV performance without having hardware that we could bring in and let people evaluate and help sell content that's necessary in the vehicle. So if we think about this, what I had just talked through, probably the natural assumption, natural question is to say, well, can't I just use our analytical assessments to targets, right? If we set targets on the left side of that last screen, if I just look at my drive unit tones and they're below target, then I'm fine, right? And I would challenge that and really say that it's not really the case. The requirements are typically pulled together in a way that they're necessary, right? You need to meet the targets, but they don't cover every driving condition. And really, most of the time, it's this, you get target overload if you set too many requirements to try to fully constrain the vehicle development. An additional challenge with that is when you have a target exceedance, right? Typically through the development, there is some form of a target exceedance. There's always a question, is it really a problem, right? If you're a dB or two over the target for your tones, is that really a problem? If it is, how much is it worth to fix that problem? So that's where actually listening to these sounds is absolutely necessary. So in the little screen on the right, if we look at the two plots, right, really generic data, real data, but presented generically. If we look at the red line, at the higher frequencies, it's higher than the green line. First question is, how bad is the red line? So people who are really experts in this area, they may be able to look at that and get a feel for and really an idea of what that might sound like. But most people don't. They just see that, okay, there's a bunch of peaks and it may or may not be a problem. So they have to hear it to know how bad is it. Then if you go to the green line, you improved it at the higher frequency, but then kind of exceeded the red at the mid frequency. Then the question is, if that was a solution, a content change, do you make the vehicle better or worse, right? You kind of trade it off one area for another, which is a pretty typical thing. So again, you really need to experience the problem. You need to listen to it and experience it to try to decide, with the program leadership, are they willing to spend the money to move from one condition to the next? And did it really improve the vehicle? Another challenge is interactions, right? And this is a kind of a little cartoon diagram on the lower left, but I think pretty typical of what happens in electric vehicles. That we set road and wind targets, so something pretty generic, this dashed black line. You'd say that's a target that the road and wind team is working towards. You might set tonal targets that would allow some slight, allow motor tones to peak a little bit over the road and wind, but not significantly enough that you would really hear the difference or hear it as a problem. And that would be considered okay with the original targets that were set. But then in this case, right, this example, and pretty typically the road and wind team goes and overachieves, right? They did better than they said they would. And you'd think, well, that's great, right? We just made the vehicle better. That's not a bad thing. Except the people developing the drive unit, they're hiding behind that masking noise. So now their tones stand up way above the masking level. So now that becomes a problem. Even though they met their targets, it might be an issue at the driver's seat. So things like this, the interactions between the different focus areas, is really something you can bring together in a driving simulator and allow you to listen to it and start to understand how do these interactions affect each other? How is a problem really a problem? How much is it worth to fix them? So these subjective assessments are really the biggest value that's done during the vehicle development, the pre-production vehicle development process. And the NNV simulator can help you get to some of those assessments. So that's where the interactive NNV simulator comes in, right? I think most of you are aware, you've seen a bunch of presentations so far that talk about how the simulator lets you bring in kind of the vehicle performance data, so how quickly the vehicle accelerates, and it lets you recreate these major touch points for both sound and vibration, right? Sound at the driver's ear, vibration at your seat, vibration on the floor, vibration in the steering wheel. This data can be based on both measured or predicted responses. But once you have that into the simulator, where you can either free drive it or set it to drive through some prescribed driving conditions, it lets you do target sighting early on. It lets you do some of these contenting discussions and decisions, right? If you add a little bit better acoustic package, how much does it really help you? Is that difference worth the cost that comes with it? But it also helps capture some of these interactions, right? If you hear a sound, but you don't feel it, or if you feel a sound or feel a vibration, but don't hear it, how do those things interact? So this multimodal interaction that comes with the NNV simulator is hugely important. So now we'll talk about a little bit about how do we bring this into the VDP, and then this naturally leads into some of the challenges associated with it. So one of the highlights I want to point at is that it's very necessary in a actual production environment, or in a typical OEM that has a whole bunch of programs and different brands that we're developing, that we streamline the process flow. So the little diagram shows that on the right side is, we'll just call it a set of CAE tools that let us take NNV sources, the paths, and predict what the response would be at the driver's ear. So this is sound and vibration data that can come into the simulator and people can drive it. On the left side is the sound design aspect, right? Where we go from a DAW kind of in studio software, develop enhancement sounds that also come into the simulator and let us drive it. And at a high level, it seems to make sense, right? It's a pretty clean process flow. But an important thing to highlight that if we look at this process and it becomes a manual process, right? If you're jumping from one tool to the next as you go through, if you're copy and pasting data, if you're taking data files and manually placing them somewhere, it doesn't scale to real volumes that we have in the automotive industry. And just a really simplified example that makes the point, I'll just walk through this, that if you think about, a typical vehicle, a very simplified vehicle, might have 10 sources, right? We'll just say there's 2 pairs of wheels right? You're going to separate front versus rear. You're going to have 2 drive units, maybe 5 components and some wind noise, right? So 10 sources. You're going to represent the structure-borne and airborne for each of them. So all of a sudden you have 20 paths. So now that's 30 pieces of data that you have to manage here. Then you're going to do it for 5 different operating conditions. This lets you free drive the simulator. And for 5 different interfaces, right? Your ears, a couple on the steering wheel, the seat pad and floor. So all of a sudden this blows up into a massive amount of data just for a single model that you're developing. Then still within that model, as you go through the vehicle development process, you start to do contenting studies, right? You answer these questions. Do you need an isolated cradle? What if you had a drive unit tone issue and you change the gear finish or the motor design? How much does that help? As you're going through mount development, things are changing, right? So each time that something changes, you have to rebuild your model. So you have to retouch a lot of this data. And then you hit the development gates, right? And then you're developing sound enhancement, which is again an iterative process. So the whole point here, you can easily see that something that looks pretty simple, we're just going to take this data and grab some different files and pull them together in the simulator, becomes a massive data handling issue. And that's just for one program. You know, if you're GM, or actually I would say even most of the OEMs, right, you have multiple brands. Within each brand, you have multiple models. Even within each model, you have submodels, right? A Cadillac versus a Cadillac V, right? It's essentially the same vehicle, but some different higher performance content in it. So you can easily see that with this presents a massive challenge. So without some form of an automated development process, without integrating all of the tools together where data can go from one tool to the next, without somebody manually copying it, without somebody manually pasting it into another place, it doesn't scale to true volumes, to real production volumes if you're doing this in a manual sense. And just to kind of really highlight it here is that the statement that touches, right? Data touches. Anytime you have to touch the data in a virtual sense. It's very inefficient, right? It takes time. Somebody has to take time out of their day and go and copy and paste that data somewhere. And it leads to mistakes. If it's a manual process, invariably somebody grabs the wrong data and puts it in the wrong spot. So then the model that you built that you thought was correct is now representing something entirely different. So this whole cut and paste model building process, it doesn't scale to a true VDP. So one of the biggest challenges that we have looking forward, one of the biggest challenges that we're trying to solve in-house, and again, I would say one of the biggest challenges that we need help from everybody, right, is how do we take these models, how do we build these N&V driving simulator models that help us for vehicle assessment, but do it in a way that's much more automated, right? Much more automated in a sense that somebody who's developing the drive unit, if they build their drive unit model, they don't have to send data via email or via SharePoint site to somebody else. Another big challenge as we look forward is realism, right? A simulator must feel right to decide to spend money to fix an issue. And to highlight this statement, and this is something that we've experienced a few times as we've been using this in some different programs, is that there's different examples where if you hear something in a binaural sense, but not in a true immersive sense with directional audio, it doesn't quite sound right. So a simple example that really highlights it is rear bias road noise, right? There's times when the road noise coming from the front of the vehicle isn't balanced with the rear. If you drive that vehicle, it feels like, in the case if you have the road noise in the back is too high, it feels like something's open in the back. It feels like a misbuilt vehicle. You can't capture that if you don't have directional audio, right? So we're unable to represent that with just a straight binaural, in a straight binaural sense that doesn't track your head in some manner. Another one is a mirror whistle, right? A mirror whistle is a very localized event. If you play that back in just an immersive event where it's coming from all the way around you, it sounds entirely different. How significant the issue is perceived entirely differently. Another one is sound staging for sound enhancement, right? One of the things we do as we develop and create sound enhancement is define where the sound should be coming from, right? If you're bringing sound enhancement in, are you trying to bring some sound from the front that moves to the back as you accelerate? Do you want the sound to be completely surrounded or coming from the lower front part of the dash? That's staging. In order to develop that, you need immersive audio. So kind of the statement that just that binaural playback that provides a good surround effect, it's a much better than straight monaural, but it falls short of this true immersive audio. But there is kind of in development some solutions for that. So there's this object-based audio format. Some of you may know some of the trade names like Atmos. Dolby Atmos is a object-based audio, or Fraunhofer has MPEG-H and Sony has TTS-X, I believe, or there's different formats that are in place right now that people are developing. But it's important to recognize that this framework, if we take that and we couple it with the ability to predict where sounds are coming from, this would allow us to simulate sound in a three-dimensional space. Once you simulate it in a three-dimensional space, then you can render it using whichever playback device that you have with your simulator. So in this case, there's, the cartoon speakers placed around the simulator, right? But there could be a speaker array all around the simulator. So somebody comes in, sits on a seat, then they play this object-based audio format in through all of those speakers. So then it localizes the sound. An alternative would be using a headset with head tracking. So if you have a headset with head tracking, you can do the same thing. But in any case, by having localized sound, now you can represent rear biased road noise. If somebody's driving it and they turn their head, they can hear, okay, it's louder behind me, so something's not right. If there's a mirror whistle from this very localized spot, we can represent that using this object-based audio. Doing that it's hugely important, right? Because as soon as we start to go through the development process, we try to convince a chief engineer, for example, to spend money to fix a problem. The question is always asked, like, how big of a problem is it? Is it worth the dollar or the $5 or the $50 that's necessary to fix it? And object-based audio will help enhance that realism, and it helps enable those decisions, right? If the chief engineer drives the model and it just doesn't feel real, if it doesn't feel entirely real, then they have a hard time really committing money to fixing the problem. So I'll leave you with that statement that integrating analytical models with object-based audio and vibration, along with the free driving capability that's within a simulator, it enables this realistic demonstration, right? So somebody can drive it, and now it starts to really feel like they're in the vehicle, and it helps enable those decisions. So with that, okay, perfect, thank you. So yeah, just in time, the conclusion, I'll just wrap it up by leaving you with that the free driving simulators provide this format that lets us virtually experience a vehicle before hardware exists, right? This is some of the programs that we started to run through our development process. It's absolutely necessary looking forward to integrate the CAE tools to allow an optimized and efficient data flow. And I truly believe that integrating true immersive audio with localization and vibration will help bring that realism to the simulations that allow decision makers to make the decisions that they have. So with that, I'll pause and see if there's any questions, or I don't know if we kind of ran against the time here. So.
Hey, Glenn, this is Gary. Can you hear me?
Yes, I hear you, Gary.
Glenn, you did a phenomenal job. I really appreciate your contribution to the conference this year. I'm going to have to ask anybody to connect with you online through the app to submit any questions. We're just a little bit long. We're going to get going with the next presentation. But phenomenal job as always. And at this time, let's go ahead and give Glenn a round of applause for his contribution. Thank you.
Thanks, Glenn. Thank you.